Welcome everybody. It's a great pleasure and honor for me to open this day dedicated to the award of the Galileo Galilei Medal 2025. And let me give a very brief introduction to the medal and to the bit of history of the prize. The Galileo Galilei Medal Award was created in honor of the founding father of the scientific method and of modern physics. And it was created when the Galileo Galilei Institute of Theoretical Physics, the GGI, was established as a national center for advanced studies of INFN through a partnership between INFN and the University of Florence. And this happened in 2018. Starting from 2019, the medal is assigned every 2 years to at most 3 scientists who in the 20 years before the date of the award have achieved outstanding results in the areas of theoretical physics of interest for INFN. And the prize is announced on the birthday of Galileo Galilei, which is February 15th. So this year we had the official announcement on February 15th. Just a bit of history. The first edition in 2019, the prize has been assigned to Joan Martin Maldacena with this motivation for his groundbreaking ideas in theoretical physics and especially for the discovery of duality between gravity and ordinary quantum field theory with the far-reaching implications. 2 years later, in 2021, the award was assigned to Alessandra Bonanno, Thibault Damour, and Franz Pretorius for the theoretical studies describing the behavior of 2 black holes spiraling around each other until they collide. A research proved to be of great importance for the analysis of the experimental data of the gravitational wave detectors, Virgo and LIGO, which discovered just a couple of years before the gravitational waves. Then in 2023, the medal was awarded to Zvi Bern, Lance Dixon, and David Kosover for the development of powerful methods for high-order perturbative calculations in quantum field theory. These powerful theoretical computational methods have been essential for comparing theoretical predictions with experimental results obtained at the CERN Large Hadron Collider. And these are awarded 3 previous editions. Now, for this year, the selection board for the prize was composed by Professor Eliezer Rabinovici as chair, and Professor Sally Dawson, Professor Joan Martin Maldacena, Professor Michael Schiffman, and Professor Michael Turner. They decided to award the prize to Professor Pierre Sikivie and Leonard Susskind, which are here today for the celebration, for their work representing humanities' persistent efforts to see and understand what may seem invisible, revealing in the process deep connections between the largest and the smallest scales of nature. In his presentation, Professor Rabinovici will elaborate more on this, on the motivation. And now a couple of words on the place where we are. which is the most natural place to award this prize, since we are in the Villa Gioiello, which has been the house of Galileo for 11 years in the last period of his life, between 631 and 642. And so the atmosphere is extremely inspiring. And in this house, Galileo actually completed the discorsi e dimostrazioni matematiche intorno a due nuove scienze. The work was then published in Leida abroad, because he was in a house arrest here in Florence. But this is very important to remind. And then I conclude with just a general idea of where we are. We are essentially here in Arcetri, and on the importance of this hill, the hill of Arcetri, where which is rich of history and and of science in the last century. We start from the highest point, the observatory, which is now of the National Institute of Astrophysics. Then coming down, there is a path connecting directly the house of Galileo to the street, passing through the observatory. And then here there is the National Institute of Optics. And here there is the building Garbasso, where the Department of Physics and Astronomy is the site of the Department of Physics and Astronomy. And here in the buildings, it is hosted the GGI, Galileo Galilei Institute of Theoretical Physics. So the activities of the GGI are carried out in this part. This is in the room where the workshops are going on, and in this part. But this is just to have an idea of the great place where we are. And given this historical richness and science, it is worth reminding that here, for instance, in the 20s, there was a strong school of physics of cosmic rays, with Bruno Rossi, Beppe Occhialini, and many others. And in the 60s, there was a famous school of theoretical physics founded by Raoul Gatto. So this is very important to remind. And for all these reasons, the Hill of Arcetri has been designated in 2013 as a historical site by the European Physical Society. This is an important thing to remark. So I conclude my brief introduction, and now I show the program of today. We will have the institutional opening by, unfortunately, the president of INFN cannot be here, Antonio Zoccoli, and Marco Ciucchini will give his presentation as a member of the executive board of INFN. Then we have Professor Marco Pierini, Pro-Rector of the University of Florence, Pro-Rector for technological transfer and cultural activities and social impact. Professor Guido Risaliti, Deputy Director of the Department of Physics and Astronomy of the University of Florence. and Professor David Caramelli, president of the museum system of the Florence University, which is responsible for all this, in particular for the Villa Gioiello. Then going to the scientific part, we will have an introduction by Professor Eliezer Rabinovici on the motivation for the assignment of the medal 2025. And in the end, we will have the lectures by the two medalists, Professor Pierre Sikivie and Professor Leonard Susskind. So I close here my brief introduction, and I leave the floor to Marco Ciuchini.
Thank you, Fulvio. Unfortunately, as Fulvio mentioned, Antonio Zoccoli, our president, cannot be with us today because we got a sudden summon by our Minister of Research and couldn't deny it. So, but I'm really happy to be here today and convey his greetings to all of you in this very special day for the INFN life. This is a very important occasion for us. I remember almost 10 years ago when this award was established. It seems a natural companion for our Institute for Theoretical Physics, the GGI, to strengthen its commitment to excellence and internationalization. And I would say that after 4 editions, and now this is the 4th, right? I can safely say that this initiative was a success. I think our medalists were all top-level scientists, and this year is no exception. And so I think that the initiative was successful. For that, I would like to thank the director of GGI, present and past, of course, the selection committee and its president that I think do most of the job, and our medalists, of course, and all of you that are here to share with us this very special day. Thank you.
Good afternoon, ladies and gentlemen. It's a pleasure for me to welcome all of you to Florence and to the University of Florence, because as already mentioned by Fulvio, we are within the Villa Gioiello, the former residence of Galileo Galilei for a short part of his life, which is managed by the university itself. So it's an honor for me to represent the university and to be part of this group of different institutions which are today presenting the prize to very estimated colleagues. So congratulations to them from my side, and also from our rector that unfortunately today is in Rome and could not attend this event. So I don't want to waste your time. We are looking forward to the lecture, to the coming lecture. So welcome again, and I wish you a nice afternoon.
Thank you, Marco. Now it's time, Marco Risaliti. Sorry.
Guido Risaliti. Okay, good afternoon, everybody. I'm here representing the Department of Physics and Astronomy at the University of Florence. Our department hosts about 80 staff, plus many others, and we more or less cover all the main branches of modern physics, from, of course, theoretical physics and particle physics, which are the ones in the strongest connection with the INFN and the GGI, but also astrophysics. I'm an astrophysicist myself, and matter physics, applied physics and so on. So I'm very happy to be here, and I want to thank the GGI for this wonderful event, and congratulations to the winners, of course. And let me just say that this is the kind of events that make the spirit of Galileo present here. So we are here, but Galileo, I think, is more present thanks to this kind of events than for just the simple fact that centuries ago in these walls he was present in person. Okay, but he's also present in spirit thanks to events like this. So thank you very much.
Thank you, Guido. Professor David Caramelli.
Hello, everybody. I'm very happy when I was very happy when Fulvio told me 3 months ago or 5 months ago, now I don't remember well, to establish this prize here, because I think it's very impressive to stay in the same house where Galileo Galilei stayed the last part of his life, of course. I'm the president of Museal System of Atheneum, and I have this role. I remember 1st of November 2024. So no lot of time. So I hope that the next year will be another time to celebrate this medal here, especially with other childs, but we have no time to move in this situation. But there are other two connections between Galileo Galilei and myself. First is that I am not a physics, but I'm a scientist, I'm a biologist. When I see on the first slide that you show us that Galileo Galilei was born in February, the 15th of February. Another very important person that was born in February is Darwin. Okay, he born in 12th of February. Unfortunately, I born in September, so this is well. Anyway, and another connection is that these years I have I will be these years because I have a project with Museo Galileo Galilei in Florence. I will start to analyze the DNA of Galileo Galilei because I was enhancing DNA, and this is a new project that University of Florence will do the next year. So I'm very happy to stay here, and now I finish, and thank you, and the microphone to you. Okay.
Thank you very much. So we can start with the scientific part. Professor Rabinovici. You have slides? No.
Okay. Let's see, where can I stand where I can see all of you? Probably here. Okay. I stand in awe each time I come to this villa in which Galileo Galilei spent time. I do not know what his height was. I found in the internet somewhere, but I can't vouch for it, that it was a meter and 51 centimeters, but its edge, which was tall for the period. But in any case, he was a giant in the sense that his discoveries extended human knowledge all the way to Neptune and beyond. His works and the works of the 2025 Galileo Galilei Medal laureates, Professor Pierre Sikivie and Professor Leonard Susskind, embody human curiosity-driven courage and audacity. It is that spirit that we are celebrating in awarding them the medal. The detailed reasons for choosing to award the Galileo Galilei Medal to Sikivie and Susskind appear in this very thick report, which was prepared by the jury. That's for you. I hope I don't mix them up. And this is for you. Thank you. It includes also the names of various of their collaborators along the way. This afternoon, I will take the liberty to present them in a larger context that includes also some of my personal thoughts. Humans whose length scale is measured in meters have the audacity to try and understand all that transpires between the Planck scale of 10 to the minus 33 centimeters and the outmost reaches of the cosmos. Moreover, humans believe they are owed, I'm not sure by whom, a concise narrative describing the laws of nature and the fundamental constituents of matter. By the way, I'm not sure if future AI will be married to this self-dedicated entitlement, but it's definitely part of our hardwiring. And it's the same hardwiring which drives humans to challenge boundaries, to find out if they are real or if they can be overcome. Crossing oceans to reach the Americas and Australia, climbing to the top of Mount Everest and crossing space to reach the moon are boundaries that humanity overcame. Some bounds are still accepted and respected. Speeding faster than light in the vacuum is left to science fiction writers. And reaching Andromeda during a human life is just starting to tease wormhole travelers. Humans are also faced with practical boundaries. It is not clear how to directly detect objects that we are weakly interacting with. This poses an invisibility challenge. Also, classically, by definition, light does not escape from the horizons of black holes, also posing an invisibility challenge, as do the patches of the sitter universe that are outside the cosmological horizon. Pierre Sikivie and Leonard Susskind had the courage to tackle some of these apparent boundaries that present invisibility challenges. They indeed succeeded to breach holes in these walls. The electric dipole moment, which is a certain specific property of a particle called a neutron, is smaller by 10 orders of magnitude than what the theory of the color interactions would allow. Why is that? Now, of course, we're entitled to pose questions, but perhaps not all of them have answers. And you can consult the mathematician Gödel about that issue. Are we entitled to expect the answer to the question of why the strong interactions seem to respect to an amazingly large extent the symmetries of parity and charge conjugation times parity called CP? Roberto Pecce and Helen Quinn offered a solution, a new symmetry that is spontaneously broken a little bit explicitly. Steven Weinberg and Frank Wilczek offered a particle to do the job, the axion. Combining particle physics and astrophysics, the large and the small, scientists found that the axion, if it exists, must couple so weakly that it becomes what seems to be invisible to experiments. When we walk, we rarely think of the atmosphere we are pushing aside. And for all we know, we could be as well swimming in some very weakly interacting matter. That was a clear boundary that Pierre Sikivie challenged. He suggested several ingenious experiments, some mixing again particle physics and astrophysics to make the invisible visible. One of the methods includes setting up an experiment involving what I would call a very sensitive radio. This pioneering work made a breakthrough, so which many others, some of them in this room, have followed, trying to find ways to detect the undetectable. I remind you that in 1964, Penzias and Wilson found out that they are listening to the cosmic microwave background music through a radio antenna installed in Holdell, New Jersey. I wish Professor Sikivie that on his radio, the axion music will be broadcast. This brings me to the second laureate, Lenny, whom I personally met 51 years ago in 1974. I'm actually not sure where he stands on the search for the axiom. For some time, he has highlighted an idea that I personally do not behoove. He was suggested that answers for some question come with a different flavor, derived from the potential existence of a cosmic landscape. It is very appropriate to bring this up here. It is a potential next revolution. The sun and the stars are not best described by revolving around the planet Earth. Our universe may not be the only one or the most significant one. This realization stemmed from decades of Susskind studying quantum field theory, string theory, and aspects of gravity and quantum gravity. In the early 80s, I recall he claimed that studying quantum gravity and surviving is as hard to survive as one round against the boxer Cassius Clay, Muhammad Ali, in his glory days. Well, by now he has survived many rounds with quantum gravity, and his response, if I would ask him, "Gee, Lenny, what happened to you?" is surely answered by, "You should see the other guy." Susskind took upon himself to examine the reality, the texture, and the consequences of a black hole having an horizon. This led him to stretched horizon, complementarity ideas, traversing wormholes, even to connections with Bell pairs or Einstein-Podolsky-Rosen pairs and measurement theory. Last I checked, I did not find his name on the list of volunteers to physically parachute into a black hole horizon. But his intellect, through his intellect, he was able to give strong indications that there is no information paradox in the presence of black holes and horizons. This required some extra rounds with Stephen Hawking and others. He made it possible for a generation of physicists to approach the horizon boundary of a black hole and beyond with less trepidation. There is an interesting tension between the very intense personality of Susskind and his finding that the physics of black hole involve important, very relaxed timescales of the order of the exponent of the entropy, of the exponent of the entropy, compared to which the lifetime of the universe is just a flicker. Back from these large and small scales to the present, where we are celebrating the achievements and the courage of two great scientists, Pierre Sikivie and Leonard Susskind, I would say the following. Galilei was asked with sneers, "Ye men of the Galilee, why stand you gazing up to heaven?" Sikivie and Susskind answer, "Because we have the courage and we know how." Thank you.
Thank you, Professor Rabinovici. So we can pass to the first lecture. Pierre, do you have the slides?
The slides.
Yeah, just a second. Okay.
Okay, great.
We should. This is the pointer, the red one, and here you move up and down.
Up here.
And down.
Anyway, so thank you very much for this amazing award for me. You know, like many of you, I was just quietly working and feeling like no one is paying any attention. And then suddenly I get the news that I get this prestigious award with Leonard Susskind. And this was really been amazing for me. And I got a lot of compliments about this. A lot of people somewhat envious that I can come to Florence and be a guest of the INFN and the GGI. So thank you. It's been very special. So I'm going to give a talk about something I did a year ago, and I'm very excited about. And I think this is very dangerous, because usually person is excited is difficult to follow. But I'll try anyway. So, let's see, how does this work? Oh. So this is my one Galileo slide, but it's very significant because Galileo, of course, was very significant. And I think it is fair to say that he started a revolution by looking at the sky and deducing from it the laws of physics. And of course, it's not enough to just look. You have to carefully reason. So in this spirit, many discoveries have been made since then. And I would like to highlight one. Oops. Oh. This gentleman is the person who discovered the first quasar. This happened actually when I was a little kid. And I remember, because it was in the news, he discovered an object that was as luminous as a galaxy, even more luminous, but appeared to be a point. And it was called a quasi-stellar object. Now, since then, many of these objects have been found. Oops, right. They're called active galactic nuclei, or AGN. They're quasars, blazars, many other names. They're extremely powerful emitters, something like 10 to the 13 times the luminosity of the sun. And they are variable on short time scales, maybe even a few hours, from which one deduces they cannot be very big. And after a little while, it was realized that the luminosity of this object comes because they are accreting surrounding matter, and basically you get enormous energy from that because it's a black hole. Okay, I went to the list on Wikipedia of supermassive black holes to give you an idea. Okay, in the mass range 10 to the 10 to the 11 solar masses, these are enormous black holes. There is listed 37, and so forth. 10 to the 9, 10 to the 10, 52. And then it goes down a little bit, and below 10 to the 6, actually nothing is found that is really confirmed and everyone agrees upon, even though people looked for it very hard. And that this is so has been beyond doubt already 2 decades, certainly. But certainly when the Event Horizon Telescope imaged 2 black holes, it was very exciting. So they saw the black hole at the center of M87, which is a powerful AGN, not so far away. It has a black hole mass of 7 times 10 to the 9 solar masses. Now, the Schwarzschild radius of this black hole is as big as the whole system, whole solar system, all the way up to Neptune or so. So it's an enormous black hole. The one in the Milky Way, its Schwarzschild radius is as big as the sun, which is pretty mighty. But it's not an AGN, it's very quiet. Now, the existence of these supermassive black holes has been a mystery, really, for a long time. And this mystery has been aggravated by the James Webb Space Telescope, which over the last few years has shown that at cosmic dawn, when the first stars form at the redshift of order 10, you have many of these, well, appear to be AGNs powered by supermassive black holes. And this is a very big surprise because there's not enough time to make supermassive black holes just right away after the first stars forms, at least not by the usual way. So to give you an idea, if you were to make a cosmic dawn out of the material there, a supermassive black hole of, what does it say, 10 to the 8 solar masses, out of the density that exists there, you have to compress a region by a factor of 1 billion. So 1 billion is easy to say, but it is similar to taking all of Italy, north to south, and equally wide and deep, and compress it into 1 millimeter cube, which seems impossible. But it is not to us to ask that it's possible, because it apparently happens. And we have to see how can one explain it. Now, the reason why this is so difficult is because of angular momentum. So the particles don't just fall into this tiny black hole straight. You know, they have angular momentum, they miss the black hole. If they have a little bit angular momentum, I like to use the symbol big L for the angular momentum per unit mass. They have a distance of closest approach to the black hole. And this angular momentum would have to be extremely small to enter the black hole. And this has been the problem of supermassive black hole formations over the last 2 decades. On this scale, the black hole, which is shown as a dot, would have to be small like an atom practically. Okay, so how much angular momentum there is usually expressed in terms of a galactic spin parameter that Peebles introduced. And the size of it has been estimated to be of order 1, say between 0.01 and 0.2. Such an amount of angular momentum that you expect from tidal torquing, actually, is always way too much to make a supermassive black hole. Now you may say, oh, but angular momentum need not be conserved, and that is right, because you can have friction. So maybe at this point it's good to think about the water going down a drain. You know, even if the water doesn't appear to turn, when you pull the plug, finally it's spinning. This is because the particles with little angular momentum go down the drain, and the ones with a lot of angular momentum cannot go down. In fact, if there were no friction, it would never go down. There would be a minimum distance of closest approach. Whereas if the liquid is very, how do you say, like molasses, has a lot of friction, it would actually go down much more easily. It would just transport the angular momentum outward more efficiently. So this idea has been tried with gas, and it's very difficult to make it work. And with dark matter, with self-interactions, and it is also very difficult to make it work. And after JWST, hardly anyone has even tried. And one of the difficulties is that if you introduce friction for angular momentum transport, you'll heat up the medium, and that will increase its pressure. Now, I'm going to claim that axions do the job. And you may ask, what's special about axions? Don't they also heat up if they have friction? And what's special about them is that the heat does not go into the condensate, but goes into the thermal distribution above the condensate. When you have a Bose-Einstein condensate, you have the condensate, and then you have a thermal distribution above it. So the heat goes into the thermal distribution above, but the condensate will always try to go to the lowest energy state, as Einstein pointed out. So I should remind me if I take too much time. No, okay. So I wrote a paper about this with a graduate student called Yushin Zhao. And maybe I read the second sentence, because that's all you have to know. We show that the rethermalization of the axion fluid through gravitational self-interactions at the time of their first collapse at cosmic dawn transports angular momentum sufficiently fast that you make at cosmic dawn these very big black holes with masses 10 to the 6 to 10 to the 10 solar masses. That's the claim I'm going to present. So here is an overdensity that we may think of at cosmic dawn. So here we have the average, the dotted line is the average density, then you have an overdensity. My colleague Jim Ipser taught me to view this in phase space, which is the right way to discuss a collisionless fluid. So I'm drawing this overdensity when the central part has expanded and is about to collapse, and the outer parts are still expanding. Oops. So in phase space, I don't know if this pointer works. Oh, here. This is the early Hubble expansion, velocity proportional to distance. This is the overdensity that I just drew. The central part has reached zero expansion velocity, and the outer part is still expansion. Later on, this curve will become this curve, and you see that the density at the center becomes very large because the whole thing is collapsing. But it doesn't make a black hole because it has angular momentum. Oops. So you may ask, what's different about axions? Well, axions are highly degenerate Bose gas. And a highly degenerate Bose gas has very large fluctuations. This point was actually, as far as I know, first made by Einstein in 1909. And at that time, there was no such thing as highly degenerate Bose gases. But there were Bose gases, and he already remarked that in the Bose gas, the particles are more strongly correlated than what we call Poisson statistics. And in the Fermi gas, they are less strongly correlated. And in fact, people like Edward Purcell pointed out that the strength of these fluctuations in density is of order the density itself when it is highly degenerate. And they are correlated over distances of order the inverse of the momentum dispersion. Okay, this is an illustration, I think, that was made by Yusin, where he put particles in a box with periodic boundary conditions, and he just populated the lowest few modes of the box. And the thing which is interesting about this is that the density fluctuates from the highest density to zero. It illustrates this thing that this is just a classical field, but actually does illustrate the fact that the density fluctuates by order itself. So, okay. Okay. So I have a few equations. Sorry, Cynthia, Judy. This is the standard description of cold dark matter, where it has a density and a velocity, and it satisfies the continuity equation and the Euler equation. And the thing that I want to emphasize about this is it pretends very accurately, but not exactly, that cold dark matter has no velocity dispersion, because it gives at every location a particular velocity. It ignores that there is a dispersion. And there is a different representation of cold dark matter, which is wave dark matter, and it's in terms of wave functions. And the wave function maps onto a density and onto a velocity. And in this case also, you're neglecting the velocity dispersion. That's the point I want to emphasize. And, okay, the velocity dispersions are not exactly zero. So I'll look at the velocity dispersions of the main candidates. There's the heavy WIMP, 100 GeV, the KeV neutrino, and the macro EV axion. And the velocity dispersions, these are cold dark matter candidates, so the velocity dispersions are very small. But the smallest is for the axion. It's extremely cold. When the velocity dispersion is low, we say it's cold. Here it's hot, because the velocity dispersion is 300 meters per second. Let me talk about this axion. Its velocity dispersion is 10 to the minus 17 the speed of light. That turns out to be similar to a few centimeters per year. But you should, like the continents, move a few centimeters per year. But you should not think of it as a particle moving, because it is an extremely long wavelength wave. So let's think a little bit about that. Oops. Okay, so here is the phase-space distribution of a fluid without velocity dispersion. The particles have no velocity dispersion, they lie on a thin line. In reality, there is some velocity. Oops, I don't know how to push it. Oops. Oh. So the line is thick. In the case of WIMPs, what does it mean? I don't know. Actually, I should point there, over there probably. It means that there are little points, little particles that are not exactly on a line, but they're a little bit off. And in that case, it's perfectly correct to ignore these small deviations. And it's perfectly okay to give the description that was given earlier. Okay, I have to point over there, right? In the case of axions or some form of wave dark matter, you should think that the particles are in different states, different wave functions with slightly different velocities. And these states interfere with one another, and they have very large fluctuations. And the result of these fluctuations is that the gravitational field fluctuates. You know, the gravitational field is given by the Poisson equation, and if the fluctuations are equal to the density, then the fluctuations in the gravitational field are given by the formula at the bottom. These fluctuations in the gravitational field will rethermalize the fluid. And the formula is given over here. Actually, we derived this formula 15 years ago almost, but now it's like a new derivation by looking at these fluctuations. So, taking this into account and assuming that this overdensity is made of axions, when it collapses at cosmic dawn, oops, I'm estimating how quickly this fluid thermalizes as a result of these fluctuations. And when it thermalizes, angular momentum is transported outward. And the formula is over here, for the maximum possible angular momentum transport. Okay, let me skip this. Okay, so here's my overdensity seen from above. The little red circle is big radii, little black circle is small radii. The blue circle is the part of the overdensity that thermalizes sufficiently fast that it can rotate rigidly. So later, the red circle will have expanded, but the black circle will start to collapse. And because angular momentum conservation means that it will spin faster and faster, but the thermalization carries the angular momentum outward. And provided certain conditions are met, you'll make a black hole. That's what we find. Now, this picture is idealized because we are actually just assuming the infall is spherical, which is actually not correct. But we can argue, I think, that it is sufficiently correct. And there are other approximations that are made. Let me not go into this. Let me just get to the punchline. Basically, what the calculation does is to calculate at all times what is the region that can thermalize sufficiently fast that the angular momentum is on the outside, and the inside is rotating very slowly and can make a black hole. As time evolves, the inside will spin faster and faster, and the region that can thermalize will shrink. And it doesn't always make a black hole, but if the initial spin is sufficiently slow, it will make a black hole. And the initial spin is taken from these estimates of the Peebles parameter. And the measure we give is J, which is a measure of how much it is initially rotating in natural units. And this is our big result, is that you make these very big black holes with the expected spin parameters, provided the dark matter is axions. Now, here I say all the virtues of this. First of all, you make the masses, the big masses, at cosmic dawn, whereas usually people had to invoke accretion and mergers later. The black hole mass is proportional to the mass of the initial overdensity and therefore correlates with the galaxy mass, which is seen in observation. Now, I was very worried about one aspect of this, because people, oops, I'm sorry, wrong way. People say every galaxy has a black hole. But the curve that I showed, actually, if J is too large, there's no black hole formed. So I was very nervous. Is it true all galaxies have a black hole? But the galaxy M33, people have looked for it very carefully and did not find a black hole. So I assumed that it was spinning too fast and did not make a black hole. Okay, so this is my conclusion. My conclusion is axions. First, as Eliezer mentioned, they solve an important problem in the standard model in the strong interactions. They explain why the strong interactions are C and P invariant. Second, and this was discovered later, they are natural candidates for cold dark matter. But for the first two virtues it has, there are other alternatives. I put them in color. But now I'm claiming with Yusin that they also explain how supermassive black holes form at cosmic dawn. And I left it blank there because, as far as I know, there's no other explanation to form supermassive black holes at cosmic dawn. So, thank you very much.
Thank you very much for the very nice lecture. I think we have time for some question.
It was so good, huh?
Any question? Sorry.
Your conclusion at the end, what property of the axiom did you use? Is it enough that any other scalar with a pseudo-Goldstone boson would also have that feature? Yes. So it's the derivative couplings that do the job, or what does the job?
So what does the job? Thank you. So the job is done whenever you have a very cold degenerate boson gas, and there is an upper limit. Right. You cannot make it too small, because if you make it too small, then it's not able to enter the black hole by just its de Broglie wavelength. That limit is about 10 to the minus 16 EV over c square. But you're right, it's not necessarily QCD axions. It's actually ALPS, axion-like particles, a wide variety of particles that are boson, highly degenerate, and very cold.
Guido Risaliti.
Thank you. So my question is there any chance, according to your estimates, that this formation of supermassive black holes through axions happen even at later stages? I mean, not just at the very beginning or even later, because I mean, if all dark matter is made of axions, there is still a lot of overdensity. There are overdensities today, and so how does it work? Thank you.
So the claim is, thank you very much for this question. So the claim is that this only works during the initial collapse, because later you have these overdensities, but now the axion fluid has, in phase space, has wrapped up and so forth, and this angular momentum transport is no longer sufficiently efficient. So it only happens at the beginning.
Can you compute when? I mean, what do you mean beginning? Because Einstein telescope will look at black holes very far. In principle, there could be an observable, which is the depth of the potential black holes.
Right, so that is also a very important question, and we're working on that. So what is the gravitational wave signal from this? Well, what we were working on is the gravitational signal from the initial collapse, because that's actually a specific property of this scenario.
What is the frequency?
And so the frequency is something that Lisa would see. And it's not like a chirp signal. I mean, we're still working on it, so I'm anticipating. And the chirp signal, you know, you have two black holes inspiring, and they have this increasing frequency, and then they finally collapse. And this collapse is more like a thumb. You know, the gravitational wave is like one big wave that comes by and then collapses. You know, it goes up, goes down. Actually, it goes up over a very long time scale. And we estimate that there's going to be very big signal, like, I hate to stick out my neck so long, but like every few days you have one of these stumps from a supermassive black hole collapse at the cosmic dawn.
If there are no other questions, let's thank Professor Sikivie again. And congratulations again, and we can move to the next lecture by Professor Leonard Susskind.
A delightful talk by Pierre. A number of years ago, hello, can you hear me well? A number of years ago, I started teaching physics in the evening for an audience which were not physicists. They were scientifically literate, they knew a lot about science, but nevertheless they were not physicists. And I decided to include in my lectures some history of science. I'm very interested in the history of it. I think of these people, Galileo, Einstein, so forth, as my ancestors. And I'm very interested in what my ancestors thought and so forth. So I learned a little bit that I hadn't known before. In particular, I read someplace that Newton was the first modern scientist. Well, if Newton was the first modern scientist, then Galileo was the last pre-modern scientist. So I decided I would do a bit of reading, not about Galileo, but Newton. I'd be able to understand Newton. He was a modern scientist, and I started reading a bit of Newton, and it was incomprehensible. There was nothing modern about it. Among other things, it was written in Latin. And the arguments were very difficult. And it also seems that Newton had a very non-modern attitude about science. He took all of his work and he hid it in a drawer where nobody could find it. Any modern scientist would tell you that's the last thing that he or she wants to happen to their work, to be hidden away in a drawer. So Newton, I found it very difficult to feel connected to. So I decided to read a bit about Galileo, which I did. Some of Galileo's arguments actually appear in papers I wrote. And what I found about Galileo, it was utterly familiar, completely modern. Not so much in the actual work, but in the attitude about science. What he was thinking, I could easily understand, and it all made sense to me. I'm going to give you a couple. Okay, what was the style that I so admired of Galileo? Excuse me. It was a style that I tend to identify with two other great physicists. One who was a close friend of mine, one who died when I was 15 years old. Einstein, of course, and Feynman. The style of physics that they had was not to concentrate on mathematics, but to visualize the phenomena. Try to think about how they looked. To get a perspective from not mathematics, but just from visualization of the phenomena. Einstein, what happens if you move along in a very fast railroad train as a light ray goes past you? Or what happens if you send a light signal across a falling elevator? These were things that almost any smart child could understand, and yet they had the most incredibly far-reaching implications. Feynman, too. What did Feynman think about? Feynman thought about particles going back and forth. Easy to visualize, and so easy to visualize that he drew pictures of it. One of the times I met Feynman in northern Canada is I drove past a truck, and the truck was covered with diagrams, which I recognized. They were Feynman diagrams. Okay? Everybody could see what these Feynman diagrams were, and that's the way Feynman thought about things. The mathematics came after the visualization. This was something that I so admired about my two heroes in physics. I never said to myself I want to be like them. I think in some ways my style is a little bit similar to theirs, but it wasn't intentional, but it's probably why I liked what they did so much. What about Galileo? Galileo's style was very similar, and of course came long before the others. I will describe one example of Galileo thinking. All right, it has to do with orbiting. You know, planets orbit stars, moons orbit planets, all that sort of stuff. And before Galileo, nobody really understood this story of orbiting. Gravity was something that always pointed toward a center, the center of the gravitating object. Nobody thought that gravity had anything to do with things going around in circles around the gravitating object. But Galileo was interested in gravity, and he was certainly interested in orbiting objects, and he realized the two of them had to go together. Here was his argument about how gravity leads to orbiting. All right, this green thing here is supposed to be the surface of the Earth with a little mountain, a small mountain. It doesn't have to be very high, 5 feet high or something like that. And somebody up at the top of the mountain has a ball and throws the ball. Well, he could just drop the ball, in which case the ball goes toward the center, the way gravity was always imagined, pulling things toward the center. But he could also throw the ball a little bit, go off on the side. It would fall, but as it fell, it would translate along the direction that it was thrown and land a little bit away from the mountain. If you throw it faster yet, it will go further around the Earth before it lands. Keep imagining throwing it faster and faster, and eventually what Galileo realized is you could throw it fast enough so that the object would circulate around the Earth and come back and hit you in the back of the head. Okay. That seems so simple and so easy that I assume he could have explained it to me when I was 10 years old. I think I would have understood. And yet, how far-reaching is it? So far-reaching, I won't even, you all know that it has to do with planets, it has to do with stars, it has to do with everything in astronomy. And to my mind, this was one of the most wonderful arguments that was ever made in physics. Note, there was no mathematics. He didn't know about angular momentum. He didn't know about centrifugal or centripetal force. So he had to make use of other ways of thinking. And that was his way of thinking. So let's applaud Galileo. I think my own style of physics is somewhat similar. It tends to rely on thought experiments, not initially mathematics. And I'm going to tell you from my own experience over the last 20, 25 years, my own experience thinking about these kind of thought experiments and where they have led. I'm not even going to tell you where they've led. I'm going to tell you that they have led a great distance. But the first one has to do with something called the holographic principle. The holographic principle is it's probably the major dominant tool in theoretical gravitational and quantum mechanical physics today. I'll tell you a little about what it is. Hologram, everybody know what a hologram is? A hologram is a picture of a three-dimensional reality, but it's encoded on a two-dimensional surface. That's the idea of hologram, a two-dimensional surface encoding a three-dimensional reality. Okay, the holographic principle, as I'm going to speak about it, was an invention or a discovery of myself and Gerard 't Hooft, the great Dutch physicist, sometime around 1994. And here's the way it went. Let's ask the question, take a region of space. It's the region inside the dotted circle. How much entropy can be there? What is entropy? Just think of it as heat if you don't know exactly what entropy is. Or how many, roughly speaking, you can almost think of it as how many particles, how many little bits of information, if you want to be technical, can exist inside that circle. Little bits here I've represented by colored dots. And S naught, S is the standard symbol for entropy. And let's suppose there is S naught amount of entropy in that region. Now we're going to do a Gedanken experiment. Incidentally, these experiments have always been things that nobody could ever do. They made enormous progress in physics. So the idea that physics can only be done by real, genuine experiments in the laboratory, that's leaving out a lot. Some of the greatest contributions in science came from experiment, all right, but thought experiments. All right, we're going to do a thought experiment now. We're going to take that dotted region and we're going to surround it by a shell of material, and now allow that shell of material to collapse, fall inward, and as it falls inward, it will eventually create a black hole. In fact, we'll choose the mass of that shell to be exactly right so that it creates a black hole whose horizon is right where the dotted surface is. So, to begin with, we have a region with an entropy, S0, and in the end, we have a black hole. Now, black holes have entropy. This is an old story. It's due to Bekenstein and Hawking and maybe some other people, that black holes have entropy. And what we know about them is that they have an entropy proportional to the area of the horizon. The horizon forms, that's the outer boundary of the black hole, and the entropy is proportional to the area. That's something of a surprise, because normally in most physics, the entropy of something is proportional to the volume of the region. But the black hole entropy, incidentally, SBH could stand either for black hole entropy or for Bekenstein-Hawking. Anything else you can think of? I don't know. But, and the entropy of a black hole is proportional to the area A of the horizon, and a bunch of constants, the speed of light, Newton constant, Planck's constant, and so forth. But the main thing is it's proportional to the area. So at the end of the day, what you have is a black hole of known entropy. Well, by the second law of thermodynamics, the second law of thermodynamics says that entropy always increases. It can never decrease. So it follows that this initial entropy in that region must have been less than the entropy of the black hole, because black hole, the entropy always increases. And so it tells us an amazing fact that the amount of entropy that we can squeeze into any region is proportional to the area of that region. Forget black holes. Now it just tells us the maximum amount of entropy we can put in there is the area. Well, if you're a theoretical physicist, you will take away from that that this region of space can be described by a system with a number of degrees of freedom, a number of elementary bits of information that's no bigger than the area of the horizon. In other words, there should exist some kind of description of this region of space, the dotted region of space, which involves a collection of degrees of freedom which in some sense live on the boundary of the region, on the dotted surface, not the bulk, not the interior. That's, I can tell you, when 't Hooft and I first said that, a lot of people, a lot of my friends said, these guys, 't Hooft and Susskind, used to be good physicists. They've lost their marbles. I assume you know what it means to lose your marbles. One or two people, including Ed Witten, were very excited about the idea and pushed it. And certainly Juan Maldacena, the first winner of this award, pushed it very hard and really nailed it. Really nailed that this is true, that a region of space can always be described by a theory that lives on the boundary of the region of space. That, I am not going to tell you all the steps that it's taken to lead to where we are now, but let me say that the holographic principle has gone from being a wild, crazy idea to a conjecture. A conjecture is much better than a speculation, incidentally. It became a conjecture, and in time it became a standard tool of theoretical physics, a tool to analyze all sorts of situations, all sorts of systems. So it's completely accepted now, and it's a tool of physics, but it began as a simple Gedanken experiment which you could try to explain to a young child. That rings to me Galileo, not Newton. Oh, I'm sure Newton was a fine physicist, but okay. I'll tell you, let's see, how much more time do I have? I don't want to take a whole lot of, let's go on with that just a bit, just a bit. Let's talk about cosmology. Cosmology is the theory of the whole universe. It is believed that the universe as we know it is described by something similar to what we call de Sitter space. All de Sitter space is, for our purpose now, is that everything is accelerating away from us. That if we look out to the distant stars, distant galaxies, everything is moving away from us. And it's moving away from us with a Hubble expansion which appears to be roughly constant with time. So everything's moving away. It could be the galaxy, the pink galaxy at the center. The other galaxies are moving away from us. And the Hubble law says that the velocity of recession of these galaxies is equal to a constant. In de Sitter space, it is truly a constant, times the distance of that galaxy from us. That's the Hubble law. Okay, now, how far out can we see? We can see only out to a distance where that velocity is the speed of light. If something is moving away from us faster than the speed of light, we can't see it. Light can't get to us. So there's a maximum distance in our universe that we can see out to, even though things may exist out beyond it. And that distance is called the horizon. It's the place where the outgoing velocities attain close to the speed of light. That's called the horizon. It's analogous to the horizon of a black hole, but it's a little bit different. In this picture here, the white region is the part of the region of space that we at the center can see. Out beyond it is beyond the horizon. Nobody can see it. The edge is moving away from the speed of light. And what the holographic principle in this case tells us, that the entire universe in the white region can be described by a set of degrees of freedom, a theory whose degrees of freedom live on the horizon, on the boundary of this region. We are busy at work trying to use this to understand aspects of cosmology. It is not yet a firm fact, as other aspects of the holographic principle are, but in my opinion, that's where we're going in order to try to understand, in particular, the quantum mechanics of the universe. Yeah, this next picture here just says, the degrees of freedom live on the horizon. Okay. I could go on with one other example of a Gedanken experiment that has had a major impact on theoretical physics thinking. It's, how much time do I have? How much? Half an hour. Oh, half an hour. Okay. Good. I will. You may be sorry you said that. Okay, I want to talk about another example of not the same kind of reasoning, but the kind of reasoning which begins with something very simple and has enormously far-reaching consequences. It could in the future be experimental physics, but today it's mostly just Gedanken physics, meaning to say thought experiments. And yet it has had, again, this enormous impact on theorists thinking about physics. All right, ER equals EPR. What is ER and EPR? Well, E, you can always guess what that stands for. Einstein, on both sides of the equation. R stands for Rosen, another of Einstein's colleagues. And P stands for a third colleague by the name of Podolsky. If you took this equation literally, it would say that P is equal to 1, but I don't want you to take it that literally. Okay, so ER equals EPR. Two different concepts really are turning out to be the same thing. What is EPR? Einstein, Podolsky, and Rosen. All right, this is something that I probably would have a little bit of time explaining to a 10-year-old. It's the concept of entanglement, quantum entanglement. Quantum entanglement is something that can happen between things that's highly quantum mechanical, very non-classical, and it's a kind of correlation. It's what Einstein called spooky action at a distance. But whatever it is, systems can become entangled in a way that has no classical counterpart. Einstein, Podolsky, and Rosen, when did they do this work? 1935. They first did. Now, as a consequence of it later, it was realized by a physicist, a colleague of mine, a colleague not at Stanford, but a colleague in Canada, named Van Ramsdonk, Mark Van Ramsdonk, that this had a huge implication for the structure of space. Here's what he said. He said, take space and imagine it's divided into two parts. What is it which holds it together? What is it that holds it together and makes the difference between two pieces disconnected and two pieces connected? And his answer was that when the space is connected, It means that the quantum degrees of freedom of space are entangled across the gap. Entanglement is the same as spatial connectivity. That's a set of words. It'll have to do, because I can't explain it any better right now. When two pieces of space are joined to form a single piece of space, the implication is that those two pieces are entangled quantum mechanically. Okay, now let's come back to black holes. The rectangle here is space, just ordinary space. The blob in the center is a black hole which formed by material falling in. It forms a kind of dimple. That dimple keeps growing. Stuff keeps falling in. That's the black hole. In the same year, 1935, Einstein and Rosen discovered a new solution of Einstein's equations. It wasn't just a single black hole. It was a pair of black holes connected by what's sometimes called a wormhole. Here's another picture of it. This is some artist's rendition of a wormhole. There's something really wrong with this. If you look, there are stars in between these two sheets, but the sheets are all of space. There's no space between. Pay no attention to those stars in there. This is a wormhole. And this was a real, genuine solution of Einstein's equations the same year that they discovered entanglement. Well, what do these two discoveries of 1935 have to do with each other? What does ER? What was ER? Einstein-Rosen bridge, the wormhole. What does it have to do with EPR, which was entanglement? And the answer was, before 2013, nobody had any particular reason to believe there was any connection. After 2013, everything. Completely connected, 100%, and to the extent where we think they're essentially the same phenomena, entanglement and wormholes. ER equals EPR is the expression that my colleague Juan Maldacena used to describe the situation. So let me just describe it a little more. Imagine space. Space, again, is this big sheet. I've got it folded over here. Why have I folded? I folded it over so that I could imagine that two places which are really very, very far from each other, going around the outside, really can be drawn next to each other, just for convenience. Imagine a bunch of particles on the left, a bunch of particles on the right. They don't talk to each other. In terms of the lower drawing, the two groups of particles are drawn near each other, but they're really far apart, because if you want to go from one to the other, you have to go around the long way. This group of particles is imagined to be independent, unentangled, no Einsteinian spooky action between them. But now what happens to these groups of particles? Each one of them separately begins to gravitate. They begin to attract each other. Not the upper ones and the lower ones, but the upper ones attract the upper ones, the lower ones attract the lower ones. What happens when a bunch of particles attract each other? Eventually they'll form a black hole. So this thing forms two separate black holes, which, although I've drawn them close to each other, are far from each other and really don't have much to do with each other. But now let's do a different experiment. Let's start all of the particles neighboring to each other. Let's shake them up in such a way as to entangle them. Shaking up a set of particles entangles them. We create a large number of entangled, thoroughly entangled particles, and then separate them into two groups, one going one way, the other going the other way. They remain entangled. Entanglement is something which doesn't decrease when you separate particles. So they remain entangled, and now you have two groups of particles entangled with each other, but very, very far from each other. Again, each one separately starts to form black holes, each of these groups, and eventually what you get is two entangled black holes. Two black holes with spooky action at a distance between them, and that turns out to be exactly what the Einstein-Rosen bridge describes. Why? Because entanglement is the same as spatial connectivity. If the two groups are entangled and they form black holes, those black holes will be connected in this case by a wormhole. I can't even begin to tell you how this has become a tool of theoretical physics, but it has. Again, it was a crazy idea which started as wild speculation by Juan Maldacena and myself, became a reasonable conjecture, and now is a tool which is even being used to try to investigate experimental consequences of quantum computers, of all things. So the point that I'm making, that I think that Galileo knew very well, is yes, experiment is terrible, and observation is terribly important to science and to physics, but sometimes great progresses can be made by thought experiments, by simply thinking of simple things which can have very, very large consequences. Thank you, and thank you for being here. Thank you.
Thank you, Professor Susskind. Any question from the audience?
Well, I've learned that the absence of questions can mean two things. It can mean you're infinitely clear, so there's no questions left, or it can mean you're infinitely obscure, so I will take it to be the first.
In this case, there's three more options.
In this area, it's about the idea related to the entropy and surface of black hole. Means in this area of gravitational wave detection, means in which also black hole means they are. So can you also a dream to connect means your idea to what these people are measuring now?
Very, very hard. You have to remember that all of these phenomena that I've been discussing are quantum phenomena. Planck's constant is a terribly small number. So it's really very difficult to imagine that the kind of experiments you're talking about that involve big, massive black holes are going to have signals which... How long will it take for a quantum effect to make itself manifest and observable for classical black holes? Well, the answer is basically the time that it takes for the black hole to Hawking evaporate. That's a long, long, long time, 10 to the 77 years for a solar mass black hole. On the other hand, as I said, sometimes these things become tools for analysis of other systems. You get to use these ideas for analyzing other kinds of systems. And sometimes, if you're lucky, a gravitational description may be useful. Not because there's real gravity going on, but because the mathematics is parallel, may be useful for studying other things. The other things that we've been talking about a lot about is properties of quantum computers, things that go on in quantum computers, which to some extent are now being analyzed by quantum computer experts by thinking about gravitational systems. So it's this transition from wild idea to tool, which is what I think we can most hope for. Good.
So I'll ask a question. This idea of ER equals EPR, it's profound, but it's also a little confusing to people like me. Produce a pair of elementary particles, a pair of top quarks. Their spins in quantum mechanics are entangled. They move apart, eventually they decay, the decay product is entangled.
You want to know whether there's a wormhole between them?
Yes. How does knowing that there's a wormhole between them help? By the way, this entanglement has even been measured. So how does knowing that there's a wormhole between them help you understand that?
So the answer is, if you had a wormhole between them, you might imagine contexts where you could send a bit of quantum information into one of them and then pull it out someplace else, okay? Entanglement, in principle, allows you to do that. Entanglement, and there's a protocol for that. Quantum computer experts know all about it. It's called quantum teleportation. Quantum teleportation is a protocol that you can do with two entangled systems where you send some information into one and it comes flying out the other. Now, it doesn't violate the speed of light and things like that, but it's a very definite protocol. Big prizes have been won for the discovery of quantum not quantum entanglement, but quantum teleportation. Thank you. Quantum teleportation, and it's a real phenomenon. How do you analyze it? You analyze it these days. One of the methods of analyzing it is by pretending, well, you start with two quantum computers which are entangled with each other. That's possible to make. You throw something into one, and you then examine the other one, and you see if anything comes out that's recognizable what you sent in. How do you analyze that? Sometimes the analysis is easy if the quantum computers are very simple. If the quantum computers are more complicated, it becomes too hard to analyze by standard methods, and one of the methods of analyzing it is by pretending that the two quantum computers are black holes. And it works. It works. There have been some experiments attempted at it. I don't think the experiments are terribly good, but there will be better experiments. So, as I said, speculations become conjectures, become tools. And that, I think, is the hope for this subject, frankly. Good. Thank you.
You're right.
So this entanglement via wormholes, is it actually in contradiction of the cluster decomposition principle of quantum field theory?
Or speed of light constraint is another way of saying it.
Yeah.
The quantum teleportation is a technique for sending quantum information. Quantum information means superpositions of states and so forth. You want to send through the channel a quantum state, which means knowledge of the coherent superposition and so forth. You can do that through quantum teleportation, but only if at the same time you send classical information from one half of the system to the other. You have to send, and the classical information sending it takes time. In fact, you never violate the speed of light. You do violate what was expected, that you could not send quantum information through the wormhole. So it's, but you know, it's worth looking into if you have any interest in this kind of things. It's too hot now for me to try to.
I don't see other questions, so if there are no other questions, let's thank Professor Susskind again. Now we can proceed with the award of the medals. I can ask the Vice President of INFN, Sandra Malvezzi.
Should I do, actually? Okay. I think it's a good idea. Mettiamo giusto la medaglia. Sì. Ok.
Attenta che cade.
La medaglia?
Sì.
Cioè la medaglia e la pergamena?
E la pergamena,
E
sì.
da chi partiamo per primo? Ok. So it is really a great pleasure and an honor to award Professor Pierre Sikivie. So please, if you come over. This is the famous West Medal, okay? And it is a pergamena. Thank you very much. Nice. So, thank you so much. Thank you. And now we can proceed with the other one. I should learn now how to manage it. Let's see if I learn properly. Okay, seems so. Okay.
This is beautiful.
Yes, it is. So, okay, so Professor Leonard Susskind, okay, and also Peter Galileo. Okay. So thanks again. Thank you very much. Okay.
Thanks. Congratulations again to the two medalists. And now we are warm enough. We can have a break outside where we can have a.
With another big applause.
Yes.